So this last part of thermodynamics is entropy and Gibbs free energy, but for now we're just going to do the entropy part of it. So a spontaneous process is something that occurs without any outside assistance. Of course, temperature and pressure is dependent, usually at constant temperature and pressure because of the atmosphere. So spontaneous processes occur in one direction only. The reverse is always non-spontaneous at those same conditions. For example, if you look at the picture here, if you're holding an eggs or two eggs and you let go, the spontaneous thing that's going to happen is that they're going to fall. However, going back and having the eggs come back into the shells and then jump back up into your hand are going to be non-spontaneous. So if we're looking here at ice water in a beaker or in a flask, sorry, and liquid water in a flask, which direction would be spontaneous? It would be spontaneous this way only if the temperature is above freezing point, 0 degrees Celsius. It would be spontaneous in the other direction if the temperature is less than 0 degrees, so less than the freezing point. However, when the temperature is equal to 0 degrees, the two states are in equilibrium. Some are melting, some are freezing. It's an equalized process. So looking at these couple examples, water at 40 degrees Celsius gets hotter when a piece of metal heated to 150 degrees Celsius is added. That would be a spontaneous process. Water at room temperature decomposes into hydrogen and oxygen gas. That would be a not spontaneous process. We don't have water randomly decomposing into its component elements. Benzene vapor at a pressure of 1 atmosphere condenses to liquid benzene at the normal boiling point of benzene, 80.1 degrees Celsius. That would be at equilibrium. Since that's at its normal boiling point, it's both going into the vapor phase as well as back into the liquid phase at equilibrium. But now moving on to entropy, we use the letter S to signify entropy. And entropy, in the most basic sense of the word, is going to be the extent of disorder or chaos or randomness in a system. The unit for entropy is J over K, which is joules per Kelvin. So it is temperature dependent. If it's positive, that means it has more disorder. If it's negative, it has less disorder, which means there's more order. For example, if we have a solid, we know that the atoms and molecules and particles are arranged in a specific pattern. They're close together. There's not a lot of disorder going on, so this would have low entropy. As we increase the temperature, we know we're adding heat, we're adding energy. The particles are absorbing that energy, and they can eventually break apart into the liquid form, where there is more disorder. So we're going to have positive entropy because now we have more disorder. And again, we keep adding heat, and eventually we're going to get to the vapor phase, which is the most disorder of the 3 phases of matter, because there's more randomness going on. So this is going to have the highest entropy of the 3. When we have a solution formed from solids, so if we have a solid salt, cube or block, whatever particle, here, as it dissolves and it becomes hydrated and it dissociates into its ions, that's going to be an increase in entropy because there's more disorder. As a solid, it's nice and organized. As it dissolves, it's going to have an increase in chaos. So an increase in entropy. If we have a decrease in the number of gas molecules, for example, there's 2 moles of nitrogen monoxide, 1 mole of oxygen, and 2 moles of nitrogen dioxide. So we have 3 moles of gases and 2 moles of gases in the product. That's going to be a decrease in entropy. There is less disorder. Some of these molecules have come together and formed a new product, so there's less disorder with less moles of molecules. So for here, we can predict entropy, the change in enthalpy, as positive or negative. If we have water liquid going to water gas, that should be an increase of entropy, as now we have more randomness, more disorder with gas molecules. If we have aqueous silver and aqueous chlorine ions producing solid silver chloride, that should be a decrease in entropy, because now we're becoming a solid and there's going to be more order, less disorder. Alright, on this next one, we have solid iron reacting with oxygen, producing iron 3 oxide, so rust. But if you notice, we have a solid and a gas in the reactants, and then only a solid in the products, which means the entropy will decrease. We'll have less disorder, more order. Here, we have all gases, so now we can look at the moles of gases. We have 1 mole of gas, 1 mole of gas, so that would be 2 moles of gas for the reactants, as well as 2 moles of gas in the products. So this one, the change in entropy is pretty close to 0. How we're to find the actual amounts of entropy changes, we go back to this famous equation. Okay, so remember, of course, the triangle is delta, S is entropy. This is in the standard state. Sigma is the sum, N is the number of moles of all the products minus the sum of all the reactants. And you get those values from Appendix C, which should have been handed out to you. So we can predict whether there is an increase or decrease for the synthesis of ammonia from elemental nitrogen and hydrogen. So here we have 1 mole of gas and 3 moles of gas here, so that's 4 moles of gas here, and 2 moles of gas in the products. So my prediction is there's a decrease in entropy because we have less moles of gas, so there's going to be more order. To actually calculate it, okay, we look at the standard enthalpies on that chart. So I find N2, it's 191.50 joules per mole Kelvin for hydrogen, and for ammonia. Okay, again, notice that it's joules per mole Kelvin. Now entropy is joules per Kelvin. So now this per mole, that means per 1 mole. Well, in the reaction, not all of them are per 1 mole. So that's where we get the multiplying by the number of moles. Okay, so it's products minus reactants. So my product, 192.5 times the 2 moles, since this is per 1 mole, times the 2 moles. That's my only product. So minus my reactants, 191.5, and it's just times 1, plus the 130.58 for hydrogen times the 3 moles of hydrogen. And I should get a negative value, as the entropy should decrease since we have more order. And I have a negative 198.24.